Hi everyone, I am Ramakrishna Kalluri, one of the TS of Medical Image Analysis course. I am a research scholar working under Dr. Ganapathy Krishnamurthy Garu in the Department of Engineering Design at IIT Madras. By the end of this lecture, you will get to know how to use GANs for medical image synthesis. Mostly I will discuss on implementing DCGAN algorithm for generating images having data distribution almost close to the given training data distribution. Mainly, I have divided the entire lecture into three parts. First one is DCGAN algorithm introduction. Second one is dataset discussion that we are going to use to implement this algorithm, dataset discussion. And the third part is implementing DCGAN algorithm using PyTorch deep learning framework in Google Colab. Let us take the first part, that is DCGAN introduction. DCGAN can be called as deep convolutional generative adversarial neural networks. GANs mainly consists of two networks. First one is generator and the second one is discriminator. Usually in many machine learning or deep learning problems, we will be given some data set. Let us take such a case and discuss the importance of generator and discriminator in GANs. Generator always try to generate fake or artificial images that are almost indistinguishable from the given real data or training data. That means the probability distribution of the generated or fake images is almost close to the probability distribution of the real data distribution. Now coming to discriminator, the discriminator's task is to just distinguish the real and fake images. Whatever the images generated by the generator are to be rejected by the discriminator continuously. Okay. So likewise they compete each other and will reach to a point where discriminator will not be in a position to distinguish between real and fake. That means at that point fake images generated by the generator are almost close to the real images. This is the loss function, or you can call objective function, that is used by the GANs. With respect to generator, this function will be minimized, whereas with respect to the discriminator, this function will be maximized. That is why people call this one as min-max algorithm. Okay. Sorry, min-max objective function. That is the basic idea of GANs. In summary, generator always try to generate the fake images that are almost similar to the data that is given in the data set, or we can say training data. Discriminator's task is to always to reject the images generated by the generator, whereas to accept the images that are present in the real images are given data set. GANs are incredibly sensitive to hyperparameters. To overcome, following guidelines will help in implementing the DCGAN. Okay. These are the 5 guidelines suggested by the authors in the paper, Deep Convolutional Generative Adversarial Neural Networks. Now if you observe clearly, in this entire DCGAN algorithm, generator will be like this, whereas discriminator will be like this. If you observe clearly, go to the first point, replace any pooling layers with striated convolutions and fractional striated convolutions with generator. Here if you observe, generators and discriminators will only contain only CNN layers. In discriminator, the CNNs are strided convolutions only, strided CNN layers, whereas in generator, we will use fractional strided convolution, or in other way, transposed convolutions, transposed CNN layers. Okay, that means all the max pooling layers or minimum pooling layers or average pooling. In any of the all the pooling layers were removed. All the pooling layers are removed. All the pooling layers are removed. Now get back to using batch normalization in both generator and discriminator. We will use batch normalization in both generator and discriminator. Okay. Next thing is remove fully connected layers also from deeper architectures. That means we will avoid using fully connected layers also. So the summary is only CNN layers are present. Only CNN layers are present in the particular network, and batch normalization is present everywhere, both generator and discriminator. And the last thing is we will use relief activation function in generator for all the layers except for the output, which uses tan h. In generator, all the other layers use relief activation function except for the last layer, where we use tan h function. The usual range of this tan h activation function is -1 to +1. Okay, that means at the last layer of this entire output, at the last layer, generator will consist of all the pixel values will in between -1 to +1, more or less like normalized images. Okay, why we generate normalized images? Because real data or the data set of the training data or the data that is generated by the generator, and this is the original real or trained data. Before passing the real data to discriminator, we have normalized all the training data images. Normalized all the training data images to -1 to +1 range. So now whatsoever the images that are generated by the generator also to be present in the same format as that of the data that is being fed into discriminator. That means the generated data by the generator also should contains all its pixel values should be in the range of -1 to +1. That is why we have used tan h function at the end of last layer in the generator. And the last point is use leaky ReLU function in the discriminator for all the layers. That means in discriminate section, all the layers will contain leaky ReLU activation function. So these are the 5 guidelines one has to keep in mind while implementing this DCGAN algorithm, so that the network will be somewhat less sensitive to the hyperparameters, so that we can expect a stable training. That is the summary. Now let us speak about generator for some time. Generator contains only transposed CNNs, and the second thing is batch normalization is present, and all relay activation functions for all the layer except for the output, which uses tan h activation function. Okay. Now what is the input to the generator and what is the output to the generator? Let us see. For the generator, in this case, they have used a 100-dimensional vector, some random noise vector will be fed into generator, so that the output generated by this generator will be a 3-channel 64x64 image. That is, we can say RGB 64 height and 64 width image. Okay. Now observe here, in generator we have fed 100-dimensional noise vector and all the convolutional transpose layers are used. At the end we will get 3-channel having height 64, similarly width also 64 image has been generated. Now let us speak about discriminator. Now discriminator will take inputs as either real images or fake images. That means the input to the discriminator will be a 3-channel 64x64 image. Okay, that means RGB, any of these images, either real or fake images, fake image generated by the generator or real images that are brought from original dataset, will be fed into the discriminator, and now the discriminator will give the probability score. The score indicates whether this particular any of this RGB image belongs to real data, that is given image being real. That is what this score indicates. Suppose the output score for any given image is very near to 1. What it means? It is a real image. Okay, there are more chances that the image that has been fed can be considered as a real image. Suppose this value is very near to 0. That means there are very less chances for the given image to be real. What we can conclude now? Maybe that image is fake image. Okay, this is how discriminator and generator will function. Now let me show you in what way generator and discriminator are designed in the network using these 5 guidelines. Suppose this code has been designed for this chest X-ray image generation using DCGAN algorithm. Here we have 2 parts like generator network, similarly discriminator network. Let me go through that one. See here, they have indicating generator network. In the generator network, if you observe clearly, they have used only convolutional transpose layers. See here, batch normalization there, ReLU activation function, convolution 2D, transpose 2D, batch normalization, ReLU, convolutional transpose 2D, batch normalization, ReLU. If you observe clearly, at every stage they have used ReLU activation function only, except at the last layer. At the last layer, they have used TANH function, which I have discussed earlier. So in generator, almost all the convolutional 2D, transposed 2D networks are used. At the same time, batch normalization is used, and ReLU activation functions are used in every layer, except at the output layer, where they have used TANH activation function. Here, if you observe clearly, I will get back to what is this noise vector and all that stuff later on. Just basic idea. This is, or in another way we can say, let me tell you. Here we are. Okay. Now let us get back to discriminator code. Okay. Here if you observe, they have used strided convolution only just normal CONV 2D layers, and leaky ReLU, and CNO TD. Okay. Everywhere they have used leaky ReLU activation function only. But at the end they have used sigmoid. That is for outputting the probability score. That is either near to 0 or near to 1. That's why they have used sigma. Since sigmoid activation functions output values lie between 0 to 1. Just as a basic idea, discriminator has been designed like this. Similarly, generator has been designed like this according to the 5 rules framed by the authors in the DCGAN paper. Now let us see what exactly we are going to discuss later on. First of all, we will set some hyperparameter values. Next thing is creating the dataset preparation and data loader preparation. In deep learning, we will first prepare the dataset. After downloading the dataset, whatsoever the necessary transformations are to be done, please do it. And later on, we will suppose the dataset contains some n images. Total n images are there in the dataset. Instead of directly feeding these total of n images into the model directly, we prefer mini batches. We prefer feeding mini batches rather than feeding the whole dataset. We will prefer feeding mini batches dataset. So that is where this data loader part will come. That means it will help you to load data in mini batches from the entire dataset. Okay. After that we will prepare the model. After preparing this model, we should initialize the weights and biases. For that, in simple way, we call it as weight initialization step. We will follow some criteria to initialize these weights. End of the day, even weights are also just numbers only. But we will put some restrictions, like we will keep all these weights or these numbers. We will take it from either some normal distribution or some particular probability distribution. That is up to us. Okay. But in the paper, they have used standard normal distribution only. But the code whichever I show you also, they have used the normal distribution only. Okay. Weight initialization. And the next step is generator network design, discriminator network design, loss functions. As I said earlier, they just prepare a weight initialization function. Later on, after designing these models, after designing generator network and discriminator network, those weight initialization function will be called on here, so that the weights and biases of these two networks will be initialized using this function. Okay. Later on, they have designed the loss functions also. Okay. End of the day, here we are using the classification only, be either the particular image being real or fake. That means we just here using binary cross entropy loss only. Binary cross entropy loss only. Later on, when we go and see the code, I will explain you there. I will show you what sort of loss function they have used. Binary cross entropy. Next thing is training loop. Since the network is designed, data loader, data, everything is designed, and the loss functions are also mentioned. Now our target is to start the training. That is where this training loop in detail will be explained. Later on, we will evaluation of the result. At the end of the training, what we will do is, using that particular model, we will generate some images from the generator, and I will compare those images with the original real data images. This is what the entire process we are going to see while going through the code. Okay. Before that, first let us focus on discriminator training. Where here real images and fake images both will be fed into the discriminator. Now its task is to classify. Okay. So what it will do is, here suppose the given input is real image, the output, the target value will be kept as 1. Whereas if you provide fake image, the image generated by the generator, at that time the target value is 0. This is how the loss function is designed there. Okay. And end of the day, we will calculate the corresponding binary cross entropy loss only. But giving these targets or maintaining these targets is very important here. While training the discriminator, we will feed both real images and fake images. Real images from the training data, fake images from the images generated by the generator. So how it will train means, the loss will be, suppose real input is given as input, at that time keep the target values as 1. Whereas if you feed the fake images, at that time keep the target value as 0. This is how we will prepare. Now coming back to generator training. While training the generator, we won't consider real images. So we only have fake images only. Fake images. Here, suppose this is fake image, but here we will give its corresponding target value as 1. That means while training the generator, we are fooling the discriminator in such a way that whatsoever the images generated by the generator, their targets are kept as 1. That means we are fooling the discriminator. This is how the target values are chosen, and later on again they will use binary cross entropy loss only. Please keep these points in mind. While going through the code, I will show you. Now let us discuss about the dataset that we are going to use to implement this algorithm. Dataset, that is chest X-ray dataset. It contains pneumonia and normal. Of 2 classes of images are there, and the data has been downloaded from Kaggle. Now let me show you that Kaggle chest X-ray images pneumonia. Just type this one in the Kaggle. You will get to know about this data. There you can see that download 2 GB of data. Just click here. The data gets downloaded to your local computer. How it will be, I will show you. Once you download to your local computer, see here. Once you download the data from Kaggle, in your particular directory wherever you have downloaded, this file will be shown. This folder where chest X-ray, and it contains 3 folders: train, test, and validation. Let us see what is there in each and every folder as a subdirectory. Let's do it. First, we have chest X-ray. Chest X-ray is the main directory, and afterwards we have 3 folders. Now again subdirectory will be there. First one, second one. Let us see. Inside the train directory, we have again normal and pneumonia. Particular class of chest X-rays. Let us see how many files are there in training data. Even while implementing this algorithm also, we mainly focus on this training data itself. Here we are not focusing on test data and validation data. Let us see how many files are there. Inside the train folder, you can see normal and pneumonia. Let me open normal. You can see this is how the images will look like, and all these images are in .jpeg format. See here. Let me count how many images are there total. 1341 items in normal folder. 1341 chest X-ray images. Similarly, let me open one image and let us show. This is how the image is looks like. You can see clearly here. Now coming back to this is how the data looks like. Let us get back to pneumonia folder. Inside this pneumonia folder, just count the total number of images. 3875 is sum total of 3875. So total images in the entire training data folder is nothing but 1341 plus 3875. That means sum of these two numbers 6 1 1 2 1 5 2 1 6. Okay, just remember this one. Once we go and use this data, we need this number, because usually for deep learning algorithms we will feed the data in terms of batches. Okay, out of this 5216 data, we will keep batch size as some 64, 128, 256 or 32. Likewise, we will give several batch sizes. Okay, suppose I take batch size as 128. Let us see in a single epoch how many iteration will be there. So 5216 total images were divided by 128. So the answer will be 40.75. So rounded up to 41. That means total images are 5216. That means one single epoch means we have to go through all the batches of images. That means on a single batch size we will say one iteration. One iteration is nothing but one single batch size. That means 128 out of these entire images, 120 images will be taken and training will be done, and we call that phase as one iteration. Similar, likewise, we have total of 41 iterations. 41 iterations. Once you take the training data, once you take the batch size as 128, now we can say that in a single epoch, in one epoch, we have 42 iterations. That's it. This is what the discussion of entire dataset. Summary is just X-ray data has been downloaded from Kraken, and we have mainly two sorts of diseases, pneumonia and two classes, pneumonia and normal. Now coming back to normal images, there are 1341 images. When it comes to pneumonia, we have around 3875. So in total 5216 number of images. So while feeding the data to deep learning model, we just divide the data into several batches. So for suppose, as an example, I have explained you here with respect to 128 as batch size. If you keep 128 batch size, so 5216 whole divided by 128, that means 41 batches. In a single entire training data, we can make 41 batches. Or in other way, the deep learning training will be happen on each and every batch. That means we have in total 41 iterations to go through the entire data set. Or in another way, we can say that in a single epoch, we are going to have 41 iterations. Why I have explained this stuff means, while implementing this algorithm, I have used batch size as 128. This calculation will be helpful for you. Okay. This is the end of this dataset discussion. In this section, we will now see how to implement the code for the downloaded dataset of chest X-rays. So here, if you go to PyTorch tutorials, here you can see DCGAN tutorial, and you can directly go there and go through this one. Okay, but let me explain you what is happening in each and every block, so that once it is done, we will directly go to our code, whatever I have written here. Yeah, but let me explain in a brief way. See here, this is the entire code. For explanation sake, taken here. See here, DCGAN tutorial. They just explained what exactly GAN is and what we have already discussed in the first part. Min-max algorithm. Now coming back to DCGAN. What they have done is, first of all, we have used the PyTorch framework. First of all, PyTorch framework. Next thing is, they have imported all the required modules. Okay. NumPy, Matplotlib. Apart from that, random torch. These are the deep learning library. Torch.nn, .nn, .parallel. All these modules are to be imported before going to write code. Next thing is, they have imported here manual seed, and usually we use random values, especially for initializing the weights or some other places. To repeat the same values, we always go for seed to keep the random value as a fixed value. Random value as a fixed value throughout the program. Okay, that means for a particular time of running, the value should not change. Okay, that is how we go for manual seed, similarly in torch and even random seed. Okay. Now coming back to the inputs or hyperparameters, whatever we are keeping here. Here you can see the data root. Data roots in the sense the root directory. Suppose here, as I have shown you earlier, here I am trying to use chest X-rays. This is the root. Chest X-rays folder is the root folder. Inside this, again I am going to train data. This is what my root folder. Okay. Inside that root folder, we have normal and pneumonia folders. This is what my, even for your, maybe for this kind of data set we have done like this. Suppose in case of your data set, you may have some root directory and you may have trained that. Instead of just X-rays, you might have some other data set. Inside this, you will definitely have this division of test, train and validation. Inside train data, you will have how many, according to your problem, you will have n number of classes, and you have to keep this kind of directory structure. Root directory, root directory, its subdirectory and its subdirectories. Okay, this is how the file should be arranged, folder should be arranged. Next thing is workers. Next thing is batch size 128. Okay, they have taken 128. Later on you can change this one and you can play around with this one. So we call this one as a hyperparameter. Next thing is image size. For the implementation check, they have used 64 by 64. Okay. I mean, even whatever data you are working on, for all the images in this particular data set has to be resized to 64 by 64 somehow. Okay. Next, number of color channels in the input image. For color channels, it is 3. Number of channels of the particular data set of images you are having. Next thing is the NZ, that is length of the latent vector. It means the random noise vector. Suppose I have already told you. In the case of generator, it takes 100-dimensional input vector here. This is called, they are saying, as latent vector. Okay. You can, here also they have kept it as NZ equal to 100. This is the number of channels of the input images. Next thing is size of feature maps in generator and size of feature maps in discriminator. Here you can keep, according to your problem at your hand, you can keep these values. But here they have kept as 64 and 64 for both discriminator and generator. I will explain you in generator section so that you will get some idea. Let me continue. Here the random noise input vector is 100 size. Here if you observe this feature maps values, we can write this one as 64 into 16. For this one we can write 64 into 8. This one we can write 64 into 4, 4, 4, 6. That's right. And again this one can be written as 64 cross 2. That means this value has been fixed. This is what I am talking about it as NGF value. Okay. The same thing will be worked out for discriminator section also. Okay. Please keep it that point in mind. Maybe this value can be changed according to the problem at your hand. Okay. But in this case, we are using this one as well as 64 only. More or less you can keep the same values only. Now coming back to NDF, similarly number of epochs. It depends, man, how many number of epochs you want to go through the entire training process. Similarly, learning rate. If you observe here number of epochs they have taken as 5 value. Learning rate has been fixed for both. For discriminator we can have one learning rate, and for generator we can have another learning rate. But here they have kept both the values as LR equal to 0.00. Sorry, one more 0 2. Later on you can play around with them, so that you can bring some modifications. So modification in the sense in terms of improvement. Okay. At the end, another thing is they have used the optimizer as ADAM optimizer. ADAM optimizer has two parameters, beta 1 and beta 2. Beta 1 has been fixed to 0.5 and beta 2, let us see where exactly they have point. See here, the optimizer D and optimizer generator. For optimizer generator optimizer and discriminator optimizer, they have used the parameters same learning rate here. Beta 1 value is 0.5 they have taken, and the beta 2 is also 0.999. Okay, these values are fixed. You can change LR value here, or later on when you play around with the hyperparameters, you can bring a lot of changes here. Okay, these are the discussion of hyperparameters. Here they have used some other data set in the tutorial section, but in our case we are going to use chest X-ray data set. Inside chest X-ray data set we have train folder. Inside the train folder we have two subdirectories. So the root directory will be this one. Okay, here number of classes. Okay, here pneumonia, and another thing is normal. Okay, nothing else. Now coming back to, okay, once you keep these hyperparameters and data, here they have shown data set organization. Now coming back to data set and data loader. These are the very important concepts. Here you can see the data root directory will be given. These are like transforms, man. I mean, you can resize the image, you can center crop the image. You have to convert the, usually the entire deep learning will be worked on tensors, not on NumPy arrays. Next thing is we have to normalize the values to -1, +1. These things will, first one indicates mean values for each and every channel. Similarly, this indicates standard deviation of each and every channel. Okay, please keep those points in your mind. This is more or less like bringing augmentation inside this one. After creating this data set, we have to go for data loader, where we will provide the batch size. Entire data set has been given here, so that 128 images will be fetched out and will be used for training. Now please keep the, suppose in case you have a local GPU at your home, or you have a local GPU, so that you can use this command. Otherwise, even in Google Colab also you can use that one. Here they have out of 128 images as a batch. Let us see, 1 2 3 4 5 6 7 8 1 3 4 5 6 7 8 8 10 8 64. Here they are bringing out some total number of, in a single, here see, real batch of 0.2 device of 64. They are extracting 64 images out of 128 from a particular batch. Okay, and they have shown here using matplotlib. Okay, next thing is weight initialization. During the earlier only I have told you we have to initialize the weights. Next thing is generator. Once we go through here, in generator section they use only transposite convolutions and batch normalization and relay activation function. At the end only they have used only tan-h function. I have already discussed in the theoretical part. Same thing has been implemented here. Batch normalization is present here everywhere. This will follow the same diagram what they have shown here. Okay, you will get to know, it's not very difficult. Next thing is, this is implementation of generator block. Here in deep learning, all the parameters, all the input tensors, or the output tensors, or even the model. Model means these parameters will come into play. everything should be in the format of tensors only. Suppose if you are using GPU, all these tensors are to be moved to GPU tensors. This is the fundamental point. Whatsoever the data you have, all those input images are whatsoever the data, irrespective of the kind of data, even text, images, any other, everything should be converted into tensors. Suppose if you are using GPU, those tensors should be converted into GPU tensors. Okay, this is what they are doing here. Now you can see 100 dimensional random noise vector has been kept as an input, 512 feature maps outside, 512, 256, 256, 128, 128, 64. At the end, you will have only 3 feature maps containing output. Okay, that is what required here. Next thing is discriminator. Same thing, here you will feed the input image as 364 plus 64, and the output will be probability, whether this particular image belongs to, at what probability score this particular image belongs to real image. That is the output of this discriminator. Same thing here also we have followed leaky relay activation functions, batch normalization, and strided convolution. Strided convolutions. Now this is the discriminator block. Earlier we have discussed about generator block. Before that we have just prepared the data set and converted into data loader in terms of batches. Now coming back to loss functions. As I have already mentioned, we are going to use binary cross entropy loss only, this loss function. Here they have used the fixed noise. Okay. This is for the sake of seeing how exactly generator is generating the images. Real label is given as 1 and fake label is given as 0. Here you can see 2 opt measures will be given individually for opt generator and discriminator. You can bring lot of changes here as you can play around with them, hyperparameters. This beta 1 value and beta 2 values are suggested in the paper actually. They have taken the same values suggested in paper. They have used the same values here. Now coming back to training. In the training section, you can see train the generator, train the discriminator, and compute the loss obtained in discriminator, loss obtained in generator. D of x indicates discriminator output when we feed real image from the data set, whereas G of z indicates output image generated by the generator and it has been fed into discriminator. So D of G of z indicates the probability score, that is output given by the discriminator when we feed the fake image or generated image generated by the generator. This is what is exactly these formulas indicate the terminology. Next thing, let us move on. This is entire, this one is like a training loop. This is entire training loop. Here with respect to generator, and this loop has been written with respect to discriminator. Okay. I have already told you in discriminator section, the real images and the target values will be kept 1. Whereas if you give fake images, the output target value will be kept 0. And the loss functions are calculated accordingly. Whereas in terms of this generator, what they do, for the fake image itself only, they keep the target value as 1. Okay. So that we are fooling the discriminator here. Using generator. This is how it goes. And the loss values, error values, everything is computed. Suppose as I have already mentioned, so in our case of data set, we have around some 58 something like 128 batches we have taken. That means in each epoch contains total of 41 batches or 41 iterations. So if you observe the results here they have used 5 epochs. For each and every epoch, we will have 40 iterations. Out of 40 iterations, we are going to see only for first one and 11th one or 10 or 20th iteration. Likewise, we will see the output. Once we go, I will show you how to run the code also. But as an explanation sake, I am saying. Now coming back to the results. Here you can see the loss functions, loss values. Okay. Discriminator loss and generator loss, both are computed here. This color indicates discriminator and blue color indicates generator loss. Okay, end of the day both the loss should decrease. Okay, now this is just for the sake of how generator is progressing by taking the input random noise vectors and outputting. See here, all these images are not completely drawn. You can see slight modifications are there. That means they are at the initial stage of training. But as you pass by, if you do very good training, all of them will come into a very good pictures later on. At the end of this training, after playing so many ways, after playing around with the hyperparameters during the training, you just have to verify the results here. Okay, here they have drawn the real images and fake images as an output. This is what shown here. This is the final thing. Okay, this is the complete explanation set. As a summary note, let me explain again in a summary. We have to import all the modules. Here we have to set the hyperparameters. Here the dataset subdirectory has to be kept in a certain format. Using this dataset and the data loader, we are going to convert entire images dataset into batches. Later on, the training loop will come: generator, discriminator, loss functions, training loop, and we have drawn the graph of generator and discriminator loss during training. And at the end, we have drawn the images generated by generator and real images that are present in the training data. That's it, nothing else. Now let us get back to code. How exactly you can use this notebook. This is the code actually. See here, I will run each and everything. Just focus. Once you open the Google Colab, you can see this one. It takes some time. You need some patience. First part is run. Here we are going to download the data set. Okay. If you observe clearly, from this link, they are downloading the data. That zip data has been unzipped here. See here, this file name containing dataset has been downloaded, zip file. That zip file has been extracted. Later on, we are going to keep the data root value. Okay, see how it goes. Let us download the dataset. It takes some time. Now you can see that after downloading the data, we have first it has downloaded the this file name. Sorry, nothing is cell data has been extracted from this particular file name. If you observe in this cell data, we have OCT, chest X-ray and code. But as of now, we just use chest X-ray dataset. And in chest X-ray dataset, my aim is just to focus on train data, train folder only. And inside, see here, this is the content to extract the subdirectory of the train. You just have to click here and copy path, and that path will be this one. Okay, so do this one. Once you download the data and everything has been done, now let us get back to setting the hyperparameters, everything. Let us run this one. Number of channels are 3 GB images. Next, NGF, NGF. Next thing is learning rate for both the optimizer has been kept as 0.0002. Later on, when we can play around, that's not an issue. Beta 1 has been kept as 0.5 for RAM optimizers. GPUs is number of GPUs are available. Suppose if you have 4 or 5 GPUs also, you can do for parallel processing also. Suppose the data set you have is very large and you have the availability of computational facility of having 4 or 5 GPUs, you can go for parallel processing. That is also be accepted. Now go for the dataset creation. Go for dataset creation. It takes some time because in batches, data loader will function in batches. Now the data loader has been generated. At the same time, we are extracting some 64 images, and they are all will be shown here. See here, all are chest X-ray images. Their original images I will show you. See here, inside the train data, normal image. See here, this is very huge in size. They are above 1,000 also, I think, size of the image. Just check once, number of pixels. Info. Here. Anyway, I have seen this one. Every data contains some 1000 by 1292930, like 4-digit numbers only, rows and both columns also. Now coming back to custom weight initialization on generator and discriminator. This is generator code. Next thing is we will convert the model of generator into GPU model. Initialization of weights are also done here. Now coming back to discriminator block. It has been executed. Similarly, discriminator. Okay. Observe here, generator. It is taking 100-dimensional input vector and outputting 3-channel image. Okay. Whereas the discriminator, it is taking the input as a number of channels cross 64 cross 64. Here we have given 3 channel only, 64 by 64, and is giving the output as probability score. See here, input as 3 channel image and outputting sigmoid. Sigmoid output is nothing but 0 to 1 rounded off to. So we are considering them as probability scores. Now discriminator block is done, generator block is done, and these models have been, both the networks have been moved to device, GPU device. Next thing, converting model into GPU device in the sense all the parameters are being converted into GPU tensors. Now coming back to training the GAN. Here we have used the loss, binary cross and triple loss only, fixed noise. This is for visualization purpose. Focus on generator. Later on you will understand. The real level is 1, optimizer and discriminator. See here, I have changed the value to, earlier in the case of discussion, I have told you both the learning rates have been kept to 0.0002 and 0.0002. But here, after doing some modifications or playing around with the values here, I came to know that maybe this value is giving somewhat good understanding of hyperparameter. So I have kept this one. But you can play around with first, you can start with both 0.002, 0.002, and later on you can do some changes to learning rate. Okay. Let me run this one. Now the final thing, training loop, generator updation and discriminator updation. Okay, see here, as I told you earlier, we have only 41 batches. Each batch contains of some 128 images. Out of this 41 also, I am in each and every epoch, I have 41 batches. I just want to I want to see the loss value at after every 10 iterations. That's why I have kept I by 10% equal to 0. Suppose if you want to see out of these 41 iterations, you may want to see for every 5 iterations, just keep a 5 value here. Suppose 20, just keep a 20 value here. So we are observing the discriminator loss, generator loss, output of the discriminator, at the same time output of the discriminator when fake image is given, and at the same time real images is given. Okay, this is how the entire thing goes on. Now let us run this value. So let us run this training loop. Let us see how the training continues. See here, this is the first epoch out of 5 epochs, and inside that 5 epochs, inside that first epoch only, we are observing the first iteration out of 41 iterations. See here, this is the 10th iteration. These are the values of loss values of discriminator and loss values of the generator. By observing these loss values, you just have to observe these values and make a decision. Fourth epoch is going on. Here I have given number of epochs as 5 epochs only. Okay, now the training has been done. Now let us see how the loss function, loss curves will be. See here, both the losses are going down. Okay, but here you can see a sudden jump of generator from the discriminator loss value. But as the days pass by, as the number of epochs increasing, since I have used very less number of epochs, you can go and change that to later on. You can play around. Let us see this progression. I mean, we are in each and every loop. These are the noise vectors, and it's corresponding. See here, you can see these images are similar to just X-ray images, whatever, but not almost close to them. But you can see those replications. Somehow you can identify them as just X-rays. Let us see for 64 images. Exactly, the output has been taken out. See here, these are all left side. You can see all the real images, whereas the right side you have only fake images. So now the entire task is done. Now our turn is to modify hyperparameters so that you should get this distribution or this chest X-ray images almost similar to these values. Then we can say that generator has been trained very well, and we can save that particular model. You can now randomly give any random noise vector to the particular generator saved model, and you will definitely get a one chest X-ray image out of it. Okay, so the entire program has been done. Now, as a summary note, I can say that it is completely for any model. Hyperparameter tuning is very important. That is where your skills matter. Now coming back to, suppose if you are, instead of using just X-ray data, you may have some other data. Okay, and keep the directories like this. Inside the chest X-ray, go to train data. Inside this, suppose you have some n number of classes, keep all the n number of classes here, and this is how the directory should be present. So I can say that the task has been done. Thank you.